Hello, and welcome back to Astronomy 104, the astronomy of planets. So far in exploring the solar system, we've studied the Sun and all the rocky worlds, the planets with solid surfaces like the Earth. They're all pretty similar to the Earth, especially Mars and Venus, where we think it was really a few relatively small but important differences that took billions of years to eventually manifest into the larger differences that we see today. As we move out from the Sun, after Mars, we get to the asteroids, which are also pretty rocky. Like the Moon and Mercury, they also don't really have atmospheres, but that's actually not surprising since they're so small that they'd have a tough time holding on to them if they had. Anyway, we're actually going to skip over the asteroids for now and come back to them in Module 10. So that brings us to the next planet out from the Sun, Jupiter. As opposed to all the rocky worlds, which only became different from one another through billions of years of evolution, Jupiter really is really different from all of them. It orbits just 5 times further from the Sun than the Earth, but is 300 times more massive. It's only 1,000th the mass of the Sun, which basically puts it right between the two, either a milli-Sun or a kilo-Earth, depending on how you look at it. You can fit more than 1,000 Earths inside of Jupiter. And then when you look at its composition, things get even more different. Jupiter doesn't just have an atmosphere of gas. It has no solid surface anywhere inside. It's 90% molecular hydrogen, which is highly combustible, so it doesn't even exist in our atmosphere. And it's about 10% helium with traces of other elements. Basically, it's got the same composition as the Sun. Those are just 2 of the weird tidbits about Jupiter. Then, another 4 astronomical units away, we reach Saturn. Saturn's the last of the naked eye planets. Its main ring structure extends 80,000 kilometers past its surface to 2.5 times the planet's radius. The rings in the planet are clearly visible with any telescope, and it's amazing to see. But the outermost ring, which is called the Phoebe ring because it comes from particles blasted off of Saturn's moon Phoebe, is so faint that it was only discovered in 2009 by the Spitzer Infrared Space Telescope. The ring is way further out than the main rings. Its radius is more than 13 million kilometers. That's 1/10 of the distance from the Earth to the Sun. The Phoebe ring is so large that when Saturn's at opposition, meaning that Earth's come around the Sun so that it's the Sun, Earth, and Saturn are all in line and we're as close to Saturn as we ever get. When that happens, the apparent width of the Phoebe ring is twice the angular diameter of the Sun and Moon. Another interesting thing about Saturn is that it's actually less dense than water, and its hydrogen to helium to other things ratio is even stranger than Jupiter's. At 96% hydrogen and 3% helium by volume, its overall composition is even lighter than the Sun, lighter than anything else in the solar system. It's actually the only planet that's less dense than water. Another big difference between Jupiter and Saturn and the planets we've explored so far is the numbers of moons they have. Mercury and Venus have no moons, Earth has one pretty big one, and Mars has 2 little asteroid-like things orbiting it. I don't even want to quote the numbers of moons that Jupiter and Saturn have, because if I do that, I'll probably have to reshoot this video every time the course is offered. The main reason that the numbers of moons of these planets is not yet very well established is that between the rings and the asteroids that are gravitationally bound to them, the numbers that could be quoted for each is actually nearly limitless, depending on the size of rock that you want to call moon. With that said, though, both planets actually have a few very large and very special objects orbiting them that are more than worthy of the title moon. Saturn's Titan, for instance, has a thick nitrogen atmosphere like Earth's, but laced with methane and ethane that condense into clouds, rain out into lakes on its surface, and then re-evaporate. A lot like water does on Earth, except that Titan's methane-ethane cycle operates at a temperature less than 100 Kelvin. That's minus 170 degrees Celsius. Titan is the only object other than Earth where we found clear evidence of stable liquid on its surface. Then there's Enceladus, which has a subsurface ocean of salty water and ice volcanoes erupting from its south pole that are the source of one of Saturn's outer rings. Jupiter's Io is also covered in volcanoes, but they're the regular kind. and with over 400 of them active on its surface right now, Io is the most geologically active object in the solar system. Jupiter's next two large moons beyond Io, Europa and Ganymede, are each estimated to have more liquid water in subsurface oceans than there is in all of Earth's oceans put together. With all this interesting activity going on around Jupiter and Saturn, you can actually start to see some similarity between these systems of giant gassy planets surrounded by geologically active moons and the greater solar system. They start to look like mini solar systems themselves, enough that you might wonder how far the analogy can be drawn between the Sun and the planets on the one hand, and the outer planets and their moons on the other. Did they form and evolve in much the same way as the whole solar system, only as a subsystem at 1/1000th the scale? And then there's the bigger question. Why did these mini solar system type planets form a bit further out while all the planets closer to the Sun are Earth-like? What is so different about conditions 5 astronomical units away from the Sun that a planet like Jupiter can form with all its geologically active moons, with their liquid water oceans and all that, compared to 1.5 astronomical units from the Sun, where Mars formed with so little mass that it couldn't even hold on to an atmosphere, let alone become one of these giant superplanets? When we studied the inner planets in the last two modules, we could compare their various subtle differences and examine how those emerged through each planet's evolution without really needing to address the origin of the Sun and the planets and how that all worked. That problem of where the planets all came from, it didn't really stand out because the Moon and the 4 inner planets are all actually pretty similar solid objects, more or less anyway, at least compared to Jupiter and Saturn. But now that we've reached these outer planets, really the main question that pops out is, why are they so completely different? And that's really where the big science question of the course comes in. See, I could tell you right now all about that, about how the solar system is thought to have formed through the gravitational collapse of a large gas cloud, which flattened into a disk with a bulge in the center where the Sun eventually formed, how matter within the disk coalesced to form the planets, and how the strong solar wind from the forming Sun drove a lot of the lighter elements from the inner part of the solar system, and that's why the inner planets are all rocky and the outer ones aren't. A lot of textbooks actually start off with this idea, which is called the solar nebular hypothesis, before going on to explore the planets. One reason they do this is it makes it easier to explain certain things right away, like why Venus, Earth, and Mars are thought to have been much more alike when they formed, and why Mercury is thought to have never really had an atmosphere. But the problem with doing things this way, though, is that the nebular hypothesis is a hypothesis. It's a guess about how we think things really happened in our solar system a long time ago, how we think it formed. And the reason we think this guess is the right one is that the natural outcome of it, if things actually happen this way, is, or should be, the solar system that we observe. In other words, the nebular hypothesis is based on what we know, on the evidence we've collected, and it gets refined along the way as we make new and unexpected discoveries. For the nebular hypothesis to be really meaningful, and to understand how it joins together all the details that we know of to produce the solar system that we observe, first of all, you really need to know what there is to know about the solar system. And that's really what we've been up to in the last couple of modules. We've been gathering evidence about all the inner planets. And in this module and the next, we're going to go on gathering all the evidence that we can about the outer planets, so that in module 10 we can put it all together and discuss the solar system's origin. Then in module 11, the last module in the course, we'll see how the nebular hypothesis stacks up against the more recent information about planetary systems beyond our own. Anyway, that's a bit of a long-winded introduction about Jupiter and Saturn and why they're interesting and where studying them fits into the rest of the course. So enjoy learning all about the two biggest planets in the solar system and their awesome moons.